task that I want to talk about is this idea of classification plus localization. So we've talked about image classification a lot, where we want to just assign a category label to the input image. But sometimes you might want to know a little bit more about the image. In addition to predicting what the category is, in this case the cat, you might also want to know where is that object in the image. So in addition to predicting the category label cat, you might also want to draw a bounding box around the region of the cat in that image. And classification plus localization, the distinction here between this and object detection, is that in the localization scenario, you assume ahead of time that you know there's exactly one object in the image that you're looking for, or maybe more than one. But you know ahead of time that we're going to make some classification decision about this image, and we're going to produce exactly one bounding box that's going to tell us where that object is located in the image. So that's that. We sometimes call that task classification plus localization. And again, we can reuse a lot of the same machinery that we've already learned from image classification in order to tackle this problem. So kind of a basic architecture for this problem looks something like this. So again, we have our input image. We feed our input image through some giant convolutional network. And this is AlexNet, for example, which will give us some final vector summarizing the content of the image. Then, just like before, we'll have some fully connected layer that goes from that final vector to our class scores. But now we'll also have another fully connected layer that goes from that vector to 4 numbers, where the 4 numbers are something like the height, the width, and the x and y positions of that bounding box. And now our network will produce these 2 different outputs. One is this set of class scores, and the other are these 4 numbers giving the coordinates of the bounding box in the input image. And now during training time, when we train this network, we'll actually have 2 losses. So in this scenario, we're sort of assuming a fully supervised setting. So we assume that each of our training images is annotated with both a category label and also a ground truth bounding box for that category in the image. So now we have 2 loss functions. We have our favorite softmax loss that we compute using the ground truth category label and the predicted class scores. And we also have some kind of loss that gives us some measure of dissimilarity between our predicted coordinates for the bounding box and our actual coordinates for the bounding box. So one very simple thing is to just take an L2 loss between those 2, and that's kind of the simplest thing that you'll see in practice. Although sometimes people play around with this and maybe use L1 or smooth L1, or they parameterize the bounding box a little bit differently. But the idea is always the same, that you have some regression loss between your predicted bounding box coordinates and the ground truth bounding box coordinates. Question? Sorry, go ahead. So the question is this a good idea to do all at the same time? Like, what happens if you misclassify? Should you even look at the box coordinates? So sometimes people get fancy with it. So in general, it works okay. Like, it's not a big problem. You can actually train a network to do both of these things at the same time, and it'll figure it out. But sometimes things can get tricky in terms of misclassification. So sometimes what you'll see, for example, is that rather than predicting a single box, you might make predictions like a separate prediction of the box for each category, and then only apply loss to the predicted box corresponding to the ground truth category. So people do get a little bit fancier with these things. That sometimes helps a bit in practice. But at least this basic setup, it might not be perfect or it might not be optimal, but it will work and it will do something. Was there a question in the back? Yeah, so the question is, do these losses have different units? Do they dominate the gradient? So this is what we call a multitask loss. So whenever we're taking derivatives, we always want to take derivative of a scalar with respect to our network parameters and use that derivative to take gradient descent steps. But now we've got 2 scalars that we want to both minimize. So what you tend to do in practice is have some additional hyperparameter that gives you some weighting between these 2 losses. So you'll take a weighted sum of these 2 different loss functions to give our final scalar loss. And then you'll take your gradients with respect to this weighted sum of the 2 losses. And this ends up being really, really tricky, because this weighting parameter is a hyperparameter that you need to set. But it's kind of different from some of the other hyperparameters that we've seen so far in the past, right? Because this weighting hyperparameter actually changes the value of the loss function. So one thing that you might often look at when you're trying to set hyperparameters is you might make different hyperparameter choices and see what happens to the loss under different choices of hyperparameters. But in this case, because the loss actually because the hyperparameter affects the absolute value of the loss, making those comparisons becomes kind of tricky. So setting that hyperparameter is somewhat difficult. And in practice, like, you kind of need to take it on a case-by-case basis for exactly the problem you're solving. But my general strategy for this is to have some other metric of performance that you care about, other than the actual loss value, which then you actually use that final performance metric to make your cross-validation choices, rather than looking at the value of the loss to make those choices. Question? So the question is, why do we do this all at once? Why not do this separately? Yeah, so the question is, why don't we fix the big network and then just only learn separate fully connected layers for these two tasks? People do that sometimes, and in fact, that's probably the first thing you should try if you're faced with a situation like this. But in general, whenever you're doing transfer learning, you always get better performance if you fine-tune the whole system jointly, because there's probably some mismatch between the features that if you train on ImageNet and then you use that network for your data set, you're going to get better performance on your data set if you can also change the network. But one trick you might see in practice sometimes is that you might freeze that network, then train those two things separately until convergence, and then after they converge, then you go back and jointly fine-tune the whole system. So that's a trick that sometimes people do in practice in that situation. And as I've kind of alluded to, this big network is often a pre-trained network that is taken from ImageNet, for example. So a bit of an aside, this idea of predicting some fixed number of positions in the image can be applied to a lot of different problems beyond just classification plus localization. One kind of cool example is human pose estimation. So here we want to take an input image is a picture of a person, and we want to output the positions of the joints for that person. And this actually allows the network to predict, like, what is the pose of the human, where his arms, where his legs, stuff like that. And generally, most people have the same number of joints. That's a bit of a simplifying assumption. It might not always be true, but it works for the network. So for example, one parameterization that you might see in some data sets is define a person's pose by 14 joint positions, their feet and their knees and their hips and something like that. And now when we train the network, then we're going to input this image of a person, and now we're going to output like 14 numbers in this case, giving the x and y coordinates for each of those 14 joints. And then you apply some kind of regression loss on each of those 14 different predicted points, and just train this network with backpropagation again. Yeah, so commonly you might see an L2 loss, but people play around with other regression losses here as well. Question? So the question is, what do I mean when I say regression loss? So I mean something other than cross entropy or softmax, right? When I say regression loss, I usually mean like an L2 Euclidean loss or an L1 loss, or sometimes a smooth L1 loss. But where, in general, classification versus regression is whether your output is categorical or continuous. So if you're expecting a categorical output, like you ultimately want to make a classification decision over some fixed number of categories, then you'll think about a cross entropy loss, softmax loss, or these SVM margin type losses that we've talked about already in the class. But if your expected output is to be some continuous value, in this case the position of these points, then your output is continuous. So you tend to use different types of losses in those situations. Typically an L2, L1, different kinds of things there. So sorry for not clarifying that earlier. But the bigger point here is that for any time you know that you want to make some fixed number of outputs from your network, if you know, for example, maybe you knew that you wanted to, you knew that you always are going to have pictures of a cat and a dog, and you want to like predict both the bounding box of the cat and the bounding box of the dog. In that case, you know that you have a fixed number of outputs for each input, so you might imagine hooking up this type of regression classification plus localization framework for that problem as well. So this idea of some fixed number of regression outputs can be applied to a lot of different problems, including pose estimation. So the next task that I want to talk about is object detection.